Today we're talking about electric potential. So this is chapter 24 of the text. And electric potential is a lot like gravitational potential. And we'll go through the formal aspects of it, and we'll talk about how how we use electric potential all the time. And it's electrical potential is potential energy, just like gravitational potential is potential energy. Gravitational potential energy acts on a mass. Electrical potential energy acts on a charge. Just like gravity, right? The potential energy comes from in gravity. The potential energy comes from mgh, right? Which is mg is the force we have to apply to a mass, and h is the distance we move it through, and that gives us potential energy. So the electric potential energy is the work per unit charge done on a charge to increase its energy. And so we have the total potential energy U per unit charge, and that gives us the potential V, right? And so for any electric charge where we have V, the potential energy is just Q times V, right? We've got our normalized potential energy per unit charge, and then we've got our total potential energy, which depends on exactly what charge we have. Changes in potential energy, just like changes in gravitational potential, right, are just governed by changes in gravitational potential energy. It's just changes in height, right? Here, it's just changes in the energy per unit charge, which we're going to call the voltage here shortly, the energy per unit charge. So delta, a change in potential is just Q delta V. So V final minus V initial. The work done, right? The work done on the particle as it moves from the initial position to the final position is opposite to its change in potential energy. And from conservation of energy, if a particle moves through a change in voltage, it gets that gets converted into mechanical energy. So the kinetic energy is also minus Q V final minus V initial, right? So if we do work on it, or if we just let it go, the work done on it by the potential it becomes a kinetic energy. So if we add it all up, change in kinetic energy is minus the change in potential energy plus any work that's done by an applied force, right? Pretty standard conservation of energy, much like what we did last semester with mechanical energy. And that's because part of this is mechanical energy, and we're just now generalizing potential to include electric potential. Now, there are, in electrical work, we always have what we call equipotential planes or equipotential surfaces. We don't really talk about this so much in gravitational energy, but if you look at the top of your desk, that's an equipotential surface, right? It doesn't matter where you put your book on the top of the table, it has the same potential energy. And so when we talk about equipotential surfaces in the electrical sense, we're talking about the same thing. Here is a surface where the potential energy for a charged particle is the same anywhere on this surface. Now, what does that mean about moving things around on that surface? Right? We haven't changed the energy of it at all if we just move it from one location to another, as long as it stays on that surface. If we want the potential difference between 2 points, right? Remember, the electric field is the force per unit charge, right? Electric field is force per unit charge. So when we have this term E dot ds, That's the force times the distance we're moving it through. Force per unit charge times the distance we're moving it through. The minus sign because we're converting this into a potential energy, and so the work we do adds to the potential or subtracts from the potential depending on which way we're going. So we take some path through here. We're doing work against the electric field to take that path, right? And that gives us the change in potential. Very often in gravitational fields, we often talk about the ground as zero, right? We could pick zero as the tabletop, and so then minus a meter would be get us to the floor, and so we'd have negative potential down to the floor. In the electric field, we often pick some point, and especially when we get to electric circuits, we pick some point as our zero potential energy point, and we go up and down from there. So here, if we just simply call whatever our initial point was our 0 point, then the potential energy at any particular point is minus the integral of the electric field dotted with ds. So we're just integrating along the path. The only component that matters along the path is the part parallel to the path. All right, and later we'll get to there's a good bit of path independence here, and so since the only component that matters, we could actually go straight up the electric field to here and then follow an equipotential curve straight over, and we get the same change in potential energy. Right? There's path independence here. Just like in the gravitational field, there's path independence. The change in potential isn't dependent on the path you take to get from one point to the other. The same thing is true here. Then, to simplify things, if we have a uniform electric field, then the change of potential delta V is just minus electric field delta X. Just straightforward. All right. So this leads to a couple of things. Let's talk about units for a second. So the electric field we think of in terms of newtons per coulomb, right? This potential is joules per coulomb, right? The potential energy V, voltage, is joules per coulomb. But this leads to, when you look at it like this, we call joule per coulomb a volt, right? We call it a volt. It's very natural to think of the electric field also in terms of volts per meter. Right? When we're talking about constant electric fields, we often express the electric field in terms of volts per meter rather than newtons per coulomb. And when we're talking volts per meter, we're really talking about, well, we've got a volt is a joule per coulomb, and we're going from there. So, if we have a simple point charge, right, and we're just going to integrate along a radial path. So, the point charge just radiates straight out. And so we're going to perform this integral from some initial position to some final position. And basically, we're going to do this from r to infinity. And the magnitude of the electric field we have is 1 over 4 pi epsilon naught q over r squared. We set v final equal to 0 at infinity, just like we do with gravity, right? When we talk about gravity in the more general sense, the zero potential point is once you've completely escaped the gravitational field. Here, the 0 point is once you've completely escaped the electric field. So you have to go out to infinity to completely escape the field. When we do this integral, V final is 0, V initial is the voltage at the point R. So 0 minus V is Q over 4 pi epsilon naught, integral from R to infinity 1 over R squared dr. So that results, integral 1 over R squared is 1 over R. And so we get 1 over r evaluated from r to infinity, and the final result here down at the bottom, all right, the final result down here at the bottom is V is 1 over 4 pi epsilon naught Q over R. So the potential energy around a point charge is that 1 over 4 pi epsilon naught Q over R. All right? And we got that by performing this integral up above. So, just like mass and just like in gravity, if we want to deal with a system of charges, well, this is simply additive, right? The electric field due to each point charge is independent of the electric field due to all the others. We simply sum up all the electric fields, or if we have potential energy, we sum up all the potential energies from each one, and that gives us the potential due to a group of charges. Now, if we have to approach a complex problem numerically, right, we divide whatever group of charge we're talking into small little point charges as an approximation, and we sum over all the point charges. Potential energy due to an electric dipole. If we have a dipole, and a dipole is, if you remember, a dipole is when you have a plus charge and a minus charge. They're balanced, and basically we're going to take the distance between them down to something very small, right? An ideal dipole, we actually take the distance between them down to 0. But here we're going to take the distance between them down to something very small. We're going to call the dipole moment the charge, right? Plus q and minus q. Dipole moment is q times the distance between them. And when we look at the dipole moment, we have r plus and r minus. All right, r plus is just a little bit different from r minus, and r minus minus r plus, the difference between those works out to be about d cosine theta. All right, it's about d cosine theta. So the approximate voltage, q over 4 pi epsilon naught d cosine theta over r squared, where theta is we let the dipole define theta for us, all right? And put theta right there, right? So we see, and we'll do it when we get to diffraction, we'll deal with exactly this same thing again, where d cosine theta is approximately that difference. So we have v equals q over 4 pi epsilon naught d cosine theta over r squared, and we just group q and d as p, the electric dipole moment. And so p cosine theta over r squared is how the voltage around a dipole goes. All right, the potential energy around a dipole. If we follow through and we work back to the electric field due to a distributed charge, we can get to the voltage or the potential energy due to a distributed charge. Right? It's just the integral of the potential energy due to each little piece. And potential energy due to each little piece is just dq over r with 1 over 4 pi epsilon naught up front. Right? So we can integrate over a distributed charge to get the potential energy from it. This is where I was talking about if we have to do this with some odd shape, we start here and do it numerically. So for line of charge, dq equals lambda dx. We've got dq over r is lambda dx over x squared plus d squared. We integrate, and we end up in the end with lambda over 4 pi epsilon naught times the log of the length of the charge, L, all right, and L squared plus D squared. D is the distance from the charge. So this is a finite charge. We're integrating from 0 to L, and we end up with the log function because it's 1 over r. So we can get this. Let me back up a second. Yeah. All right. So we've got this integral of 1 over x squared plus d squared to the 1/2, right? And that just ends up being the log that we have here. We're going to integrate over a charged disk that has a uniform charge on it. We can look at dq as the charge density times the area of a small little ring, right? That's what this is. dq is the area of this 2 pi r prime dr prime is the area of a small little ring. And when we do dv is dq over r, we stick all of that in. We integrate r from 0 to r. Now one of the things this has done implicitly is this 2 pi r is the integral around, right? It's already built in. The way they constructed this integral, the symmetry is built in. Now if you wanted to start with just a little bitty wedge, and say, well, what's the area of that wedge? The area of that wedge is r d phi dr, right? So we would have r d phi dr, right? R d phi dr, and we just integrate from 0 to 2 pi. So they left out one of the dimensions. They immediately took care of the symmetry in this, because when we integrate, there's no dependence on phi, right? So that integral over d phi simply becomes this 2 pi that's right there. All right? So this actually started out as a two-dimensional integral over the surface, and they collapsed it right away to a one-dimensional integral by taking just doing the 2 pi, the integral over 2 pi, and sticking it out front. So here's our integral. Integral from 0 to r prime dr over z squared plus r prime squared. And the result is just square root of z squared minus r squared minus z. All right? And so from this integral, and we may go over these more in lab, right? But from this integral, we get, okay, the dependence is on z, right? On z is z squared plus r squared square root minus z. Now, as r goes to as r goes to 0, right? This goes to 0. That's a good thing. Now the other thing you note from this, all we got was the potential up and down from this. We didn't do the harder problem. This does not include the harder problem of what's the potential off over here, right? So it's just the potential up and down along Z. Oop. Now we can work back the other way to get the electric field from the potential, right? Just to say that the electric field is minus Q dV, and so we get the and we've got the E dot ds, so whatever the angle there is, E cosine theta minus dV ds. So E cosine theta is the electric field in the direction of ds. So we can really write this as the partial derivative. Have you guys seen partial derivative? Didn't respond fast. Have you guys seen partial derivatives? Anybody not seen partial derivatives? There's not a big mystery. It's just we're taking the derivative of this with respect to s and ignoring other variables. Right? Treat other variables as if they're a constant when you're doing a partial. So, potential energy of a two-particle system, 1 over 4 pi epsilon naught Q1, Q2 over R. When we add in 3, we simply have to add in the other pieces, right? It's summative. They're independent. Just add up the pieces, the energy from each. So, for a conductor, electric field inside of a conductor is what? 0, right? Whenever we have a conductor, the electric field inside of it is 0. Why is the electric field inside a conductor 0? Because charges freely move. An electric field applies force to charge. So if there's an electric field inside a conductor, charges move until the charges have moved to the surface and have completely canceled out the electric field on the inside. Right? So you get a surface layer of charge that's completely canceled out the electric field on the inside of the conductor. So if the electric field on the inside of a conductor is 0, what does that say about the potential energy inside the conductor? Not 0. It is all the same. So whatever the potential energy at the surface is, that's the potential energy inside the conductor. Does that make sense? The conductor is like a tabletop. It's a level surface, right? There's no gravitational field moving you around the tabletop. And since there's no gravitational field moving you around the tabletop, the potential energy is the same all over the tabletop. So once you're inside a conductor, there's no electric field moving any charges around. The potential energy inside the conductor is all the same. Now that doesn't say anything about how high the table is, right? So it doesn't say what the potential energy is. It just says that the potential energy is the same all over the conductor. All right, just kind of a review. Potential energy, we're calling this voltage. All right. Voltage, just like with gravity, volt. Just like with gravity, it is You have to do work on an object to move it up in a gravitational field, and that gives it potential energy. So it's minus the work you do per unit charge. We thought about gravity in terms of potential energy. What would your gravitational potential energy be? It wouldn't be, or the equivalent of voltage for gravity would be GH, or minus GH, right? You leave the M out because we do it per unit mass. And we don't really normally cast gravitational fields in terms of per unit mass, but it's the same thing here. We have a force field, it's a vector field that we've normalized to per unit charge. We could talk about gravity as a force field that we normalize to per unit mass. We can get mechanical energy out of this by letting a charge accelerate through a voltage. It's what we do in high energy physics all the time. We accelerate small charges through a voltage to accelerate them up to near the speed of light. The potential energy is just the charge. Remember, voltage is energy per unit charge. So if you want to know the absolute potential energy of a charge, you just multiply up times its voltage. Change in potential just depends on the voltage, so it's path independent. We can have a change in potential plus work done, so standard conservation of energy. If there's no mechanical energy involved, then it's just work applied as Q delta V. And we can find the voltage from the electric field by integrating over the electric field through a path. And that gives us the difference between, that gives a potential difference between the end of the path and the beginning of the path. Potential energy due to a point charge, 1 over 4 pi epsilon naught Q over R. If we have a collection of them, we just add it all up. Dipole moment, right? We just have a dipole moment over R squared, and cosine theta. Again, cosine theta is the angle between the dipole. Now we often represent dipoles as a little arrow. That gives us the axis of the dipole. Cosine theta is with reference to the axis of the dipole, right? So theta is with respect to the dipole axis. Now what does that say about the potential energy for a dipole when you get to 90 degrees? It's 0. A lot of things are dipoles in nature. Water is a dipole, right? So it has a potential energy that looks something like this, although it's not a clean 2-point dipole like this. Continuous charge, you just integrate over the charge. We can also do the partial integral over a path to get the electric field along that path back out. And the potential energy to a system of charges. All right. We just, again, just like here, if we have more than 2, we just add everything up, right? Q13, Q14, Q15, we just add from each one to get the total potential energy. Okay. I believe that's the end of this set.